In this video, we'll continue going in through Chapter 4, looking at Section 4.4. 4.4 has several topics. We're going to go through quite a bit, and this can be a little bit of a frustrating and difficult section. When we start Section 4.4, we're going to introduce what we call Chebyshev's theorem, and then we will follow that up with the empirical rule, which I referred to this one before. Some people call it the 68, 95, 99 rule, and you'll see why that is in a few minutes. Both of these are still going back to that combination of the mean and standard deviation, trying to look at, again, how you could use those to talk about the spread of data. But what's frustrating for some students is that there's a lot of numbers going around, that when we're looking at these two, the theorem or the rule, that we're already looking at numerical data sets. And then in those numerical data sets, we're putting those data sets in order. And then we're talking about the percentages of data. So we're already looking at numerical data, and then we're talking about percentages. So there's just a lot of numbers that can get thrown around. And again, can just be a little confusing. So be very clear as we're moving through. Actually, before we even start, let me just give a quick reminder about percentages. So if we had 80 people or objects, and we knew 70% of those people or objects, did what we wanted. They worked properly, they believed in the same scenario as we did or something like that. They agreed with a statement. But the point is that we can combine them to then ask, how many? If I know 70% of all the people support the latest stimulus package, so then if I go and look at a group of 80 people, how many of those support that stimulus package? And again, that's just one example. It doesn't matter the stimulus package, any other example. If I know 70% of a particular group are currently in college, well, then I grab 80 of those people. How many of them should I expect to be in college? So the way to do this, the way to get this how many, is always to just look at the percentage times the total. So here, 70%, we would treat as the decimal 0.7 times, don't use an x here. We already use x as a variable for a lot of different places. So either use like the little star symbol if you really want for times. Even better to just use parentheses. So we get 0.70, which that one happens to be the same as just 0.7, times 80. And if we do that, this one works out very nice in that we get a clean answer of 56. So in this situation, if we had 70% of the people believed in something or 70% of the people did something, we look at 80 people, so how many? We would have 56 people or objects did whatever we were considering here. Another quick thing that'll come up, if 70% of the people liked, well, then that would leave 30% of the people either did not like or did not know. There's a little bit of an idea of complement. We'll talk about that later on in Chapter 6 when we discuss probability. But just to get to this how many. This comes up again. We do a lot of percentage, and we'll focus a lot on that on the video. But a couple of the homework questions just put you a little further, and that's the idea. The second part here, this is not always going to work out so cleanly. Let's just pretend instead of 80 people, we had 83 people. So now I do that same computation, 0.7 times 83, and now I get 58.1. This is where we will also start to include the word approximately. Because again, it's not always going to be so perfect. If we have exactly 100 people, 70% would be 70. And in this example here, we're lucky that this percentage came out to be a complete whole number. But a lot of times we'd have situations like this. So again, approximately how many people would we expect agree with that statement? You get 58.1. Well, you can't have 0.1 people or 0.1 objects. So that would just be rounded off to 58 people. I mean, there are situations like this one I'm rounding down because the decimal was less than 5. You know, there are situations if this was 58.7, I would have rounded up to 59. There are a few situations where it's like you would naturally have to round up. Like I've always seen this problem, like, you know, you have this many students, how many chaperones do you need for this field trip? And you get like, well, I need 58.1 chaperones. Well, you have to round up. You can't have a chaperone who has too many students, so you'd have to round up regardless of the decimal. Again, I don't want to go crazy with that. I just wanted to make this basic point so that as we get percentages, but then we know how many people or objects, we could always convert that to figure out how many are doing what we want, how many are in a group, how many fall between these two totals, how many people scored between a 75 and an 80 on the test, how many people are between 5'6" and 5'10" tall. So that type of situation. So that's where we start. We start off with two rules that start talking about the percentages of data. That when we know the mean and the standard deviation, we can start approximating the percentage of people or objects, the percentage of our data that fall between those two values. That's the big first part of this video. But then the second part, we also want to compare an individual data item to the rest of the data set. That is going to be the secondary thing that we do in this section. And for that, we will introduce something that we call a z-score. And we'll also see z-scores can be used for even more. Z-scores, again, a nice way to compare. How did I do compared to everybody else? How did I do in my athletic competition? How did I do on that standardized test? How did I do compared to my coworkers? Maybe it's talking about sales, or if I'm in a factory, how did I do comparatively on the assembly line? Things of that nature. And this will also allow us to compare data items from different sets. You work in a factory, I work in customer service. How can we compare who's better at their job? Or you're a weightlifter and I'm a runner, or you're a baseball player and I'm a basketball player. How can we compare who's better at their individual sport or at their individual skill? How can we compare when we're doing different things? So that's where this will come in. So again, this is a fairly lengthy section that has several components to go with it. 4.5 will be very quick. We'll just have a few quick things to say. But again, you really see this chapter has really built a lot. We've got a lot of numerical analysis, just getting through basics of mean and median, then expanding and being able to talk about a standard deviation, then our box plot and 5-number summary. Again, we keep building and just seeing what can we do with data once we have it, and then how do we use this information. The mean and median, giving us an idea of what's in the middle, what's common, what's in the center. The standard deviation, trying to tell us about our data, how close it is, how spread out it is, a way to compare different data sets. Again, we keep going, and we're seeing more of that here. So, a lot of information so far, but now let's really get started. On, page 175 in our book, at the bottom, they introduce, our book calls it Chebyshev's rule. Other books call it Chebyshev's theorem, same thing. We'll introduce Chebyshev. Chebyshev is a person's name. He's the person who came up with this. He's a mathematician who studied statistics. And Chebyshev's rule says that if k is some number greater than or equal to 1, the percentage, formally in our book, they call it the percentage of observations, but we could also just talk about that as the percentage of our data. The percentage of our data that lies within k standard deviations from the mean is at least 100 times the quantity, 1 minus 1 over k squared percent. This extra times 100, just even when I went up here, a lot of us already know the shortcuts, percentage to decimals. The decimal is right here. Move it 2 places to the left, your percentage became a decimal. If you have a decimal, move it 2 places back to the right, and now you're back to a percentage. Some people look at that, moving the 2 places to the right, that's the same thing as multiplying by 100. So some of us just ignore that, recognize this gives us a fraction, which is a decimal, which we can convert to a percent. Other people like to include that as that makes it a percentage. But here's the thing, everybody. That, I'm focusing on this little formula that we get at the end, but what is this really saying here? We're saying that if we take all of our data, put it in order, so I'm just stacking. All these are just little points that I'm stacking, indicating my data in order. So here's an x-axis. I don't even care what the numbers are, but smaller numbers are on the left, bigger numbers are on the right. And what maybe we're talking about height, just so at least we have some basis here. We're looking at height of men in inches. So not feet inches. So someone who's 5 foot 10 inches, we'll just say that person is 70 inches tall. So just to put a number on here, so there's 70, there's 60, there's 80. And again, just dot plot. I'm just putting dots. Wherever I find a guy, how tall are you? I put your dot on your exact height. So dot, 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 dot. So lots of dots. The truth is, this is one of those situations that if I fit a full curve, this would be one of those bell-shaped distributions where, again, most people fall somewhere in the middle, and the further away from the middle, the people who are much shorter, the people who are much taller, you get fewer of those people. So that's the kind of situation we're looking at. Now, this is a coincidence that this is bell-shaped. It doesn't have to be. But what this is saying is, if we find the mean, which for men, I should have drew this slightly. Let me just change this a little bit. Because for men, the middle is actually 69 inches. So let me just change this. Let's pretend this was 65 inches. Then this is 75 inches. This is 55. Just to make this more accurate to how that actually works with actual men's heights. But now, if you take that mean, so that means we already have to know what the mean value is. Either it's already given to us, or it has been computed, or it's something we need to compute. But if we go within 1 standard deviation, that would be k equals 1, or 2. Let's really focus on k equals 2 and k equals 3. So if you go within 2 standard deviations of the mean, so the standard deviation is a distance from the mean. So let's pretend if that length is the standard deviation, that distance in both directions, that's 1 standard deviation of the mean. Here's the mean in the middle. Here I subtracted 1 standard deviation, and that gives me a data value. And then I'd add 1 standard deviation, and that gives me another data value. Subtract the standard deviation 1 more time, add the standard deviation 1 more time, and now I'm looking at these data values. I went 2 standard deviations in the mean, and when I say within 2, I went 2 below and 2 above, and now I'm looking at the percentage of data that is here. I'm getting at least this percent. So if k is 2, 2 squared would be 4. So this would be 1 minus 1/4 is 3/4, which is 0.75. So this would become 75%. So if I take the mean and the standard deviation, I didn't give you the standard deviation total here. Again, we'll get some actual practice with this in just a couple of minutes. But this idea is just if we go within 2 standard deviations of the mean. So I would have a lower bound and an upper bound based on height. So for example, something like roughly, there are at least 75% of men who are between the heights of, this would roughly be about, what would this be? About 63 inches up to about 75 inches. We would get at least 75% of men have a height between those two totals. That's how this works. But again, it doesn't have to be this pretty. You know, maybe this is height, and height is that bell shape, that normal distribution, but it doesn't have to be. If I'm looking at test grades, let's say our class, we've got 80, 90, 100, and we've got lots of good students who have scores up here. And I've got a few scattered people out here. So most of the class did well, right? All these points. That person got 100. That person got a 99. That person got a 99. That person, I've got all these people lined up. But this is definitely not bell-shaped. Actually, I shouldn't put this person up high. There's nobody below them. So all these, just one person got an 78. One person got a 70. One person got a 67. One person got a 62. Several people got an 80. This person got an 80. So I've got lots of people up here, but then a few scattered people down here. This is not bell-shaped. If I had to fit this curve, this would be left skewed. But same situation. The mean, well, where is the mean here? I'm not going to do the arithmetic. I didn't actually give you data values, but the mean is maybe somewhere up here. But same situation. If you go 2 standard deviations above and below, if you go 2 standard deviations above to 2 below, you might get everybody on this upper side, right? If you go 2 standard deviations above, maybe now we're saying, okay, an 82 was the mean grade. So going 2 standard deviations below to above takes me to a 62 to a 102. Nobody even got 102 and nobody got above that grade, but there are people who had people below a 62. So we don't have the nice symmetry. That's the point I'm trying to make up here. We don't have the nice symmetry that we had here, but in this situation, we'd still know at least 75% of the students had a test grade from 2 standard deviations below the mean to 2 standard deviations above. If you do this with k equal 3, 3 squared is 9, so 1 minus 1/9 is 8/9. 8/9. It's a decimal that goes on forever. So this becomes 88.8 forever percent. So roughly 89%. So at least 89% of the data values fall within 3 standard deviations of the mean. So notation. I'm doing this with 3. I could just as easily do it with 2. But if you take the mean, x bar or mu, sample or population, doesn't matter. Subtract 1 standard deviation, then subtract it again, then subtract it a third time. Here's a data value. X bar minus 3 standard deviations, or mu minus 3 standard deviations. That would give you kind of like a left endpoint. And then x bar plus 3 standard deviations, or mu minus 3 standard, plus for the right side. That's how we're establishing this left and right. And if we do it with 3 standard deviations, at least 89% of your data. And again, for 2, at least 75% of your data. So this starts to come back to that general rule I talked about, the spread. How do you know? How do you use the standard deviation with the mean to really have a sense of your data? And I always talked about 2 standard deviations. Going 2 below to 2 above tells you where most of your data, gives you a window that you could understand that most of your data falls between those two values. But what does most mean? Well, now we're seeing if you go 2 standard deviations, you're getting, again, at least 75%. At least 3 out of 4 values, if not more, fall between that window. That's why we said it's not a set in stone rule, but if you go 2 standard deviations, you always get the idea most. 75%, at least 75%. In any situation, that covers most of the data. So that's all I want to say about Chebyshev. There are a lot of people who could still look at this and say, I don't get it. What's the point? And the point is what I keep emphasizing here, that this is really the 2 computations that come up. You can do it for fractions as well. If k is 2.5 standard deviations, 2.5 standard deviations above or below. But this is the point. It's just that simple. If you have this value, if you have that value. But empirical rule, that's the one we can use and we can get a little more out of. So that's the one we're going to focus a little more on. Empirical rule comes up on page 177 in our book. So I'll come back and say a little bit more with regard to Chebyshev, but again, I'm going to really focus on this. Similar type of information. Empirical rule is going to talk about the approximate percentage of data values within so many standard deviations of the mean. And you'll see in just a moment why this is also referred to as the 68, 95, 99 rule. Because the way this works, approximately, the first, and this is the most important caveat, the empirical rule can only be applied when our data is normally distributed. We've slightly mentioned this already, mentioned this idea of bell-shaped distributions. A normal distribution, not every bell-shaped distribution is normal, but all normal distributions are bell-shaped. There are a couple other bell shapes that are almost normal, approximately normal, and that we can get away using the normal distribution, but that's stuff we have to discuss further down the road. But the point of normally distributed, and again, we'll see a lot more of this, both the mean and the median, that they line up together directly in the middle of your data, and that we have this perfect symmetry. Half, well, again, that's the idea of the median. Half the values are below, half are above, but that the mean exactly corresponds. So you get a perfect 50% of the data is to the left, 50 is to the right, and again, it's all perfectly proportional. That is where we are going. So, if you know that the data is normally distributed, not all data is. That's why I brought up this second point. That is definitely not normally distributed. And we don't guess if something is normally distributed. That is a very huge hint that we'll see going forward. When you see these problems and you see somewhere in that middle of that word problem somewhere and the data is normally distributed, that is a huge flashing sign. And now, at this point, it basically means use the empirical rule, but later on we'll see some other things that come up. But that is huge. That is the only way the empirical rule can be applied, is if you have a normally distributed data set. If your data fits what they call the normal bell curve. So that's the only little synonym that could come up. Instead of saying normally distributed, they might say the data goes on the normal bell curve or the normal curve. But all that tells us the same thing. So what is the actual rule? There's 3 pieces to it. But again, have to know the normally distributed because that gives us this nice symmetric Bell distribution. And then we get approximately 68% of the data falls within one standard deviation of the mean. And then the second part. This is all going to sound basically the same. It's just we go how many standard deviations and we go to the next percent. 68% if you're only one standard deviation away from the mean. Then we go up to 95% if you're within 2 standard deviations of the mean. And then we go up to 99% within 3 standard deviations of the mean. The book actually shows it's 99.7%. So, I mean, you're talking about basically everything. So, how does this work? Well, first, the book gives us this quick little description on page 177, but then draws this diagram to follow up on page 178. And it takes the bell curve and shows all these little, gets the notation, and shows how you can break up these percentages. So, I think for a lot of people this is enough, but for other people this little diagram is how they make this work. They just keep applying the empirical rule to the new particular data set. So again, I've got my X bar in the middle. Here is some data value. If I have my bell curve, so let me try and do a nice job drawing it. Notice the bell curve. You don't spike it into the ground. You get like a little bit of a flattening off as you go to the 2 extreme sides and the nice bell in the middle. So if we've got that mean, if we go 1 standard deviation in either direction, so this is a distance of 1 standard deviation. The standard deviation is the same inside a data set, so it's not like I go up 3 and I go down 2. If I go up 3, I go down 3. There is a big chunk of my data. How much? Approximately 68% of my data falls between X bar minus 1 standard deviation and X bar plus 1 standard deviation. I could use the population notation as well, but I'll just stick with the sample notation. So X bar for the mean, S for the standard deviation. So the full 68% from here to here, but again, we've got nice symmetry. If this is a total of 68%, well, this chunk that's below the mean is equal to this chunk that's above. So if it's 68% in total, that means I could divide that in half and have 34% in either one of these half sections. If I only go from the mean to below the mean by 1 standard deviation, or if I only go up by 1 standard deviation, I can use this to know I get half of the 68%, which would be 34%. And the book just keeps expanding this. If you go out another standard deviation in both directions, well, now this would be X bar plus 2 standard deviations. This would be X bar minus 2 standard deviations. And from here to here, that's an even bigger chunk of your data. How much is that chunk? Now we're up to 95%. But again, all the symmetry that if it's 95% of my data from this x coordinate to this x coordinate, from this numerical value to this numerical value, well, half of that goes from the mean to here, and half of that goes from the mean to here. So half of 95 would be 47.5%. But if I know 47.5% go from here to here, and 34% goes from here to here, that leaves me with 13.5% here. And same thing on the other side. And then they stretch it one more. You go out one more standard deviation. Now this would be X bar minus 3 standard deviation, X bar plus 3 standard deviation. And look, Just this tiny, tiny little piece left. Just this, we refer to this as the tail region. Just this little tail region is all that's left. And that tail region is just a tiny little 1% combined. So once again, notice, everything here, everything in empirical rule completely matches up with what we said with Chebyshev, but we just get more. Instead of saying at least 75%, well, at least means 75% or more. Well, if we know it's normally distributed and we go out 2 standard deviations, it's not at least 95%, it's approximately. So 95% is more, a lot more than 75%. But now again, it's not a guessing game. It's not like it's 95% or more. It's very roughly 95%. So you go out 2 standard deviations, once again, at least 3/4, at least 75% from Chebyshev, about 95% according to empirical. That still fits that old general idea of going 2 standard deviations below to 2 standard deviations above gives you most of your data. Okay, so all of that tries to confirm that's why a couple of standard deviations above and below, that gives you a window to see where most of your data lies. But now let's get some more practice using this idea. Again, it really comes down to these 3. So, my first example, let's say we look at the number of text messages sent by the 10th grade students at North Shore High School. And we find that this data, so we're looking at the number of text messages, and this data is normally distributed with a mean, the number of text messages sent last week, just to keep one single week. The number of text messages sent last week. So we're looking at all the 10th graders in this school as my population. How many text messages did you send last week? That's our entire data set. The data is normally distributed with a mean of 37 texts and a standard deviation of, let's say, 8 text messages. And now I'm going to ask you several questions. Number 1, what percentage, approximately, what percentage of these students, of these 10th graders, sent between 29 and 45 text messages? I'm going to do several pieces here, but let's just start with this one first. We're going to ask several questions. Couple of things. Our problems are getting a little longer. Almost everything has at least some description. We're often given data or given some description about that data, but a few key things to pick out. You see the normally distributed. Like I was saying a minute ago, that's such a big clue. At this stage in the game, that's almost a guarantee that you're being asked something about the empirical rule. It's not the only possibility, but it's a very strong possibility. What makes it even more clear is the percentage question. You're being asked about a percentage and you're given normally distributed. I mean, that's got to be such a clear sign that that's asking you to use the empirical rule. So how do you use it? Well, now we need to concentrate on this window that was given to us. What's so special about this data value compared to the mean And then separately, this data value compared to the mean. What's so special? Well, let's see. The big thing is, how do these numbers compare to the mean in terms of the standard deviation? So I can notice 29 is 8 units lower than 37. So that is, this is the mean, this is the standard deviation. 37 minus 8 is 29. So 29 is the mean minus 1 standard deviation. You could put the 1 in if you like, or just only having an S, we assume the 1 is out in front. And then similarly with 45, what's so special? Well, 45 is 8 units bigger than this. 45 minus 37 is 8. So there's that 8 again. That's not a coincidence. Later on, this is what I keep saying. Later on, we'll have more tricks with the normal distribution so that these differences don't have to work out so cleanly. But at this stage, they do. They have to be this perfect. So 45 is exactly 8 more than 37. So that's x bar 1 plus 1s. That's exactly what we're describing here. You could look at it inside this diagram. And again, for some people, this is gold. And all they do is at every single problem, they keep remaking this, but then they fill in all the values. They say, okay, the mean is 37. The mean minus 1 standard deviation is 29. The mean minus 2 standard deviations, well, 29 minus 8 one more time is 21. Subtract 8 one more. I mean, they fill everything in for every problem. If you need to do that, that's fine. It works. If we were in person and you were taking this, as a timed exam in class, I would say that's a good way to run out of time. So, at home, you can get away with a little more in that sense. But what I would hope is that all you have to do, see this. 1 standard deviation below, 1 standard deviation above. That is exactly what is being described here. And that is why this first answer is 68%. But let's keep going with that. It's only one problem, and it's not always quite that simple. Let's do number 2. Approximately. By the way, I want to focus on the percentage. I think that's the big thing. But this is where, let's just put question 1A. If we sampled 127 10th graders, approximately how many sent between 29 and 45 texts last week? This gave me the percentage, so this would just be a part 2. Do what I just showed you at the very beginning on that very first page of the notes. You know the percentage from here. They gave you the total, so you would just do 0.68 times that total. This does not work out cleanly. This comes out to be 86.36. So we'd say approximately 86 students sent between that number of texts. So I'm going to keep focusing on the percent questions. But again, any in the book or any potential on a test, that if I expand it and then ask how many of these students, how many of these objects, get the percentage first, then use the total to do this little computation. But now, continuing, approximately what percentage of the 10th graders, I'm just going to shorten the question just a little bit so I could fit it, approximately what percentage sent between 37 and 53 text messages? And I'm going to do number 3. We'll see in a moment that 2 and 3 are very similar. Approximately what percent sent between 21 and 37 text messages? Once again, This is where, how much do you need to write down? A lot of people don't need to do much, and this is where certainly some people can just do this in their head. But just again, so what are you looking for? I'm again looking at these two values. But what's different about number 2 compared to number 1? These two values, well, this one was below the mean, specifically 8 units, 1 standard deviation below the mean. This was above the mean, was bigger than the mean, specifically 1 standard deviation bigger. So we had the full spectrum, 1 standard deviation below to 1 standard deviation above. But in number 2 and number 3, one of the values given is the mean. So this is the mean. Well, let's just keep going to the next one. What's so special about 53? 53 is bigger than the mean. How much bigger? It's 2 standard deviations bigger. It's 16 units bigger. 16 units is 2/8, 2 standard deviations. This is where the common mistake people saw here, 1 standard deviation, they say 68%. Now here they see 2 standard deviations and they go 95%. That is incorrect. It's 95% if you're within 2 standard deviations. Some people even here, they make the note. Saying within specifically means 1 below to 1 above. Within 2 standard deviations, 2 below to 2 above. Within 3 standard deviations, 3 below, 3 above. To make that very clear what it means to be within. This is not within 2 standard deviations. This is only 2 standard deviations above. Similar to number 3. 37 was the mean. What's so special about 21? 21 is 16 units smaller, so that is the mean minus 2 standard deviations. So if I asked you what percentage of students sent between 21 and 53 text messages, that would be just like problem number 1, except you'd go 2 standard deviations below to 2 standard deviations above. That would give you the full 95%. But here, you're not getting the full 95. You're only going, in number 2, the 2 standard deviations above the mean, and in number 3, you're only looking at the 2 standard deviations below. So this whole thing is 95%, but both of these you're only getting half. 95% giving you the full spread, 2 standard deviations below to 2 above, but in both of these situations, you're only getting half. Okay, third problem. I'm sorry, well, technically number 4. But number 4, using the same example, and then we'll do one more. We'll do a completely fresh example. Point out, these are all nice whole numbers. They don't have to be. We'll point that out in just a few moments. So, number 4, let's just finish up one more here. Approximately what percentage of the students sent more than 45 texts? This is where I think a lot of people like the picture. I mean, the first problem was so perfect that a lot of people just right from the empirical rule can get this answer. The second one, plenty of people, once they get comfortable, they don't need to draw the picture. They understand the idea of only getting half. Only going, it's not just 2 standard deviations. It could be 1, it could be 2, could be 3, but only going above the mean or only going below the mean. So not getting the full spread, but only getting half. Only going above or only going below. And then you get the half values. But then you get a situation like this. What percentage sent more than 45 text messages? Well, we already saw 45 was 1 standard deviation above the mean. So we had the 34% here. But that gets me to 45 texts. I want these people out here. So this is where more symmetry comes up. And this is where I also started to mention a little bit about the idea of the complement. If you look at every single data value, that would be 100% of the total data. So breaking this up into percentages, all of this has to add to 100. So just going from the mean to one standard deviation above, we already saw the 34%. Everything below the mean is 50%. So look at this. Two ways to do this. If I said what percentage sent fewer than 45 texts, we'd be looking at these people and we'd add these together. And we get 84% of the population, 84% of your students sent fewer than 45 text messages. Well, that leaves 16% to send more than 45 texts. I think this last one is definitely the hardest. And I could easily do this with a less than. If I said what percentage sent less than 29 text messages, it would be the same thing, but over on this side. So if I said, again, we did the problem, and I'll give you a whole fresh example in just a moment, but if we did percent less, fewer, then let's even do 21 to get into the second example. 21 is 2 standard deviations away from the mean. So that means 95%, 2 below to 2 above. Cut that in half to just get this section. Fewer than 21, I'm looking for these people. Greater than 21, I'm looking at all of these people, 47.5 plus the extra 50%. That would be 97.5% of these students sent more than 21 texts. So who's left below? You don't need the full 100%. Some of you just use half. All of this has to be 50%. So 47.5% is here. That leaves 2.5% right here. And that would be the answer for percentage of students who sent fewer than 21 texts. Okay, so like I said, empirical, I think it's important enough, and for a lot of people, it's difficult enough that it's definitely worth us going through a whole separate example. So now let's do this next one. Let's use distance traveled. Let's think we have a bunch of runners. They're preparing for a marathon. And so we look at how far they ran last week. And find the data is normally distributed with a mean of, we'll go 20.6 miles and a standard deviation of, we'll go 3.4 miles. A lot of information given. A couple of tiny little things. Sometimes instead of saying with a mean, they'll use the literal word average, but we understand that in statistics, that idea of average is the same thing as mean, so not to be fooled by that. There's no synonym. There's no way to hide the standard deviation. So these two values are given. Realize we already spent a lot of time talking about the importance. So if you were really starting from scratch, you'd have to already have these values computed. But since we do already have them, now we can jump in. And again, already notice your notation. So there's your X bar. There's your S. Again, we're just thinking of sample. Population would be mu and sigma. But this is just a bunch of runners. It's not all runners. So that's why it's just a sample. But now we could start asking some questions. So number one, what percent, approximately, I need to keep including that, approximately what percentage of our runners ran between, what is this? I want these numbers to work out nice. So let's go between 13.8 and 27.4 miles last week. Again, everybody, it's the same thing. Just because we have decimals, no big deal. What's the connection between this number and the mean? What's the connection between this number and the mean? We could just look at the differences. Well, this is smaller than the mean. This is bigger. But how much smaller? How much bigger? Well, 20.6 minus 13.8 is 6.8. And notice 6.8 is 2 3.4s. So this is 2 standard deviations lower than the mean. And then similar here, 27.4. Now I'm bigger than the mean, so I'll do this minus this, but I still get the same 6.8. So this one is 2 standard deviations bigger than the mean. 2 standard deviations lower to 2 standard deviations bigger. A direct application that gives us 95%. So 95% of our runners ran between these 2 distances. Again, it's a pretty big gap, but that's not our purpose. We're making that direct comparison. Number 2. If we surveyed 1,500 runners, approximately, how many ran between 13.8 and 27.4 miles? A complete follow-up. We already figured out these 2 distances give us 95% of our runners. So now we'll just take that 95% times the total. This one is very nice in that it comes out as a whole number. So we've seen sometimes it does. Whether it does or not, it still is an approximate. We shouldn't be surprised if we had 1,423 runners who ran between these, or 1,430 runners. It's still an approximate, but it's a very, very good approximate. So that was the only catch here. Just to take it from a percentage into a total, it's that how many question that we started the video discussing. But now number 3, approximately what percentage of our runners ran between 17.2 and 20.6 miles. And then I'm going to do a few other follow-ups. Number 4, approximately what percentage ran less than 17.2 miles. And then number 5, ran more than 17.2 miles. Starting number 3, 20.6 is the mean. So you're not getting the below and above the mean. One of these values is the mean. Well, what about this one? That is 1 standard deviation lower than the mean, right? 3.4 is the difference between these two. So I'm not at 68%. I'm only looking if I had one below to one above. There is the 68%, but we're only going from the mean to the below. So there's my 34%, and that answers number 3. Number 4, now you're not even getting 2 values. So now this less than, more than, now you're kind of looking, well, which tail, which way am I going? 17.2, well, that's 1 standard deviation lower than my mean, and I want everything less than that. So again, the couple of different possibilities. Some people like to answer number 5 first because they can look at the 34 here, that this whole right side from the mean is 50%, so that you get a combined 84% who ran more than 17.2 miles. And then if 84% ran more, well, that leaves 16% here that ran less. That really is that idea of a complement. Again, we'll keep talking about that a little more, but if you only look at 2 possibilities, yes or no, more or less, when you only have those 2 possibilities, then you could always get, well, either you have to be in one category or the other. I know yes or no questions, sometimes there's a third option of unsure, don't know, but if you only have those 2 possibilities, they have to combine to give you 100% of your data. But for this one right here, some people don't need the right side, they're just entirely focused over here. This is entirely less than the mean is 50%. We already found out 34% are from here to here, so that leaves you the 16% in that tail. Okay, so that is quite a bit on both empirical and Chebyshev, but we're still not finished, everybody, because we still have 2 more pieces left. The next component is that of a z-score. And like I said at the beginning, now we're not looking at we're still looking at a data set, but now we're starting to look at an individual data value. How do you compare? A simple little situation. You and your friend are in 2 different classes, and you both took an exam. Mary is in one class, and she got an 84. Jack is in the other class, and he got an 81. They're in different classes. So we can just try and look at these as just scores and say, oh, it looks like Mary did better than Jack. But what about compared to the rest of their class? Let's say Mary is in let's just make this up, this is a history class. She got an 84, but on your history class, the average grade was an 86. Jack is in a math class, and on this math test, the average grade was a 78. So just looking in this way, in this new comparison, you try and compare their test grades directly. Well, they're different tests, so it's probably not best to compare them head to head. You can try and say, well, it looks like Mary did better than Jack, but a better way would be to compare not head to head, but how they did compared to the rest of their class. And in this simple scenario, Mary did lower than average, Jack did better than average. So comparatively to their classes, Jack did better compared to his class than Mary did compared to hers, even though Mary had a higher head-to-head score. So that is a real easy way to get confused because there's a lot of comparisons that are going on, but that's what we're trying to get at. And I tried to make this first one easier in that she scored lower than average, he scored better than average, but it's not always quite that simple. If Mary, just if I make this change, if Mary's class had an average grade of 82, now she did better than average and Jack also did better than average, so now it'd be even harder to compare. But that's where a z-score comes in. A z-score is all about distance. It's trying to look at how a data value compares to the mean in terms of how far away it is in terms of standard deviation. So it's a simple formula. Just notice my z. I make a print z like that, but for some people that looks similar to their print 2. I put a tail on my 2, so it's not as difficult, but I still, even though my z looks pretty different than my 2, I still like that little slash through just to really, really highlight it's a z and not a 2. But that's entirely your choice. Don't worry too much about that. But the formula, our book describes the formula. I wish they gave us the symbols, and I'll do that here. The z-score for a data value is that data value minus the mean divided by the standard deviation. That's it. That's all there is to it. If you have population data, You just have the population mean and the population standard deviation. But notice, you always start with the data value. It's not big minus small here. It's data value minus the mean. So if the first example, when the average was an 86, Mary would go 84 minus 86, you would end up with a negative. A negative z-score just means that you are below the average. If you get a positive z-score, that just means that you are simply above average. That's all there is to it. So it's a simple computation. If you apply this formula back to these problems, you can use 29 and say, okay, 29 minus the mean divided by the standard deviation, you get minus 8 divided by 8 is minus 1. This data value that was 1 standard deviation below the mean has a z-score of negative 1. If you do that same thing with 45, you get positive 1. So again, I was just saying, the z-score, it feels so similar to what we were doing here, but before we were kind of doing a little more blind, just subtracting the two and noticing the common 8. Or down here, noticing that 53 is 16 bigger than 37, and that's 2 standard deviations. But all these endpoints, to make the empirical rule work nicely, to get this perfect setup, you're always just going z-score of negative 1, z-score of negative 2, z-score of negative 3. You're looking at the specific data values that are exactly 1, 2, 3 standard deviations lower than the mean, or 1, 2, 3 standard deviations higher than the mean. So that's why, that's the way, that's what we needed. That's how I should say it. That's what we needed for empirical rule to work that nicely. That we're getting those data values that are exactly 1, 2, 3 standard deviations above or below the mean. But as we go deeper, that's not always going to be the case. So let's stick with that text message example. So let's, reminder, so we had text messages sent last week. We needed the normally distributed information before. Here, it's just a little extra, but I'll still include it with an average of, 37? Yep, 37. And standard deviation of 8 messages. Find the z-score for someone that sent, we'll do 3 of these. We'll do number 1, we'll find out the z-score for somebody who sent 40 text messages. Number 2, the z-score for somebody who sent 50. And number 3, the z-score for someone who sent 25 text messages. Your data value still has units. Your z-score is unitless. That's why in a few more minutes, this is a pretty lengthy video and we still got a little bit more to go, but that's why in a few minutes you'll see that you can use this to compare different data sets because the z-score is unitless. So here we would just do 40 minus 37 divided by 8. Just careful with your calculator, everybody. If you enter that all at once and don't use parentheses, that is not the correct answer. You either do 2-step, then divide by 8, and we get a z-score of 0.375. You can put in the leading 0 if you want. Later on, we'll talk about that we'll need to round these to a second decimal. But at this stage, just whatever you get, you get. Sometimes you have to round because the decimal goes on forever. But here, no reason to cut off, so just to keep the whole 0.375. If you do it all at once, just make sure you use your parentheses to make it clear. You're subtracting everything on the top and then taking that total divided by 8, and there's that same matching value. So it's a simple computation. Same for the next. 50 minus 37 divided by 8. No big deal. Same thing. 50 minus 37 divided by 8. And I get 1.625. Both positive, so both above average, but just a little above 0, just a little positive z-score. This data value is closer to the average, to the mean, than this one is, that had a bigger positive z-score. So just some simple little things to realize. The third one, again, everybody, one of the biggest things. This is not big minus small. It's data value minus mean. Now the data value is smaller than the mean. So what? You get a negative answer, divide by 8. We get negative 1.5. The negative is important. Don't ignore that negative. That negative is a clear indicator that this is below average. Now, below average is not always a bad thing, everybody. It's easy to just say, okay, bigger is better. And in a lot of situations, higher test score, that's better. Here we're talking about text messages. Is sending more better? No, there's no better or worse here. This is just evaluating data. Maybe, maybe you have to pay more money because you're spending too much. There's situations that might make better or worse, depending on more or less. But there's no clear this is better or worse. Again, it's just about comparing. If we were running a race, you'd want to have a negative z-score. If the average time to complete the race was 37 minutes, you took 50 minutes, you were slow. Someone who took 25 minutes, they were fast. So it's not always a positive z-scores are better. We always have to take the connotation of the problem. And the last thing we can do here, before we make two comparison problems, the last thing we can do is go in reverse. How many text messages are sent if the student had a z-score of 2.5. It's just the reverse. The z-score formula is very simple, and it's already solved for z, but here, you're being asked for text messages. You're given the value of z, you're being asked for the value of x. So here we have to solve a little bit. Some people, algebra, they'd rather solve algebraically before they plug in. I'd say most people tend to prefer to plug in, though. Z, we don't know x, so we leave that as x, minus, we knew the mean, we knew the standard deviation, and that they'd rather solve for x and do it numerically. Instead of solving generically and getting a new formula and plug in, and then solve here. How do you solve this? Well, a lot of people like to think of this as over 1, so they could just think of cross multiplying. 8 times 2.5 is 20. 1 times the quantity, x minus 37, is still x minus 37. How do you finish solving for x? Well, that's attached by subtraction. I do the opposite and add. I'd get 57 equals x. But the last thing, what is that 57? In this problem, that is 57 text messages. So easy to forget the units, everybody, and lose a silly point on a problem for just forgetting something that simple. Z-scores, unitless. That's all there is to it. Doesn't matter if these are text messages or these are minutes or these are dollars. When you do this, all the units would cancel. Dollars minus dollars divided by dollars, the units have canceled. So Z is unitless, but if you solve for X, you still have units. Okay, last piece here. Again, pretty lengthy video here, but the very, very last piece. Let's see how we can use this for comparisons. So let's do a quick little height comparison. Michael Jordan is 6 feet 6 inches tall, which, just to keep it in inches, that is 78 inches tall. Rebecca Lobo is 6 feet 4 inches tall. So just directly looking, Michael Jordan is clearly taller than Rebecca Lobo. But certainly if we recognize that men are taller in general compared to women, let's compare their heights with respect to their gender. So height is normally distributed. And these numbers are actually accurate, everybody. For men, the average is 69 inches with a standard deviation of 2.8 inches. For women, the average is 63 inches with a standard deviation of 2.5 inches. Compared to their gender, who is taller? This doesn't say use z-score. Maybe it does. Maybe it says find z-scores for Michael Jordan and Rebecca Lobo compared to their gender, and then use this to determine who is taller. They may say something like that, but they don't have to. This is where we need to realize this is what z-scores can be used for. The previous page, the previous problems, much more friendly. Specifically saying, find the z-score, find the z-score. Very direct, specific questions. But now, this is where that understanding of this is how a z-score can be used. So I look for both of them. For Michael Jordan, he would be 78 minus 69 divided by 2.8. Oh, by the way, very quickly, just going back to the empirical rule, what we are seeing here, again, you have normal distribution to be more than 3 standard deviation above or less than 3 standard deviation below. That's pretty extreme. That's, a pretty good outlier. Again, we can go use that whole specific definition of an outlier, but that's a pretty good outlier out in that vicinity. And we'll see both of these people are very tall. Z-scores over 2, over 3, those are very, very high values. Those are people much above. So just to have a little bit of a number sense, we do this arithmetic and we get Michael Jordan. Again, this goes on 3.214, blah, blah, blah. So just to round off, and 2 decimal places. Down the road, you'll see exactly why, but 2 decimal places is a safe bet to round your z-scores. So he is more than 3 standard deviations taller than average. Again, he's a very tall man. But now, when we look at Rebecca Lobo, she is 76 minus 63 over 2.5. We end up getting 5.2. She is very, very tall. That is an extreme z-score. That is pretty, pretty rare. Again, we realize that, basketball players are very tall in general. So to see, and, just a little comparison, a man who is literally taller than this woman, but compared to their gender, she is so much taller in comparison. So that's all you need. You don't need an extra answer to this. The z-score is enough. You don't have to re-explain that. That would be enough to conclude Rebecca Lobo is taller compared to their gender. And let's do one more. So like I said, that very, very first one, just looking at 2 test scores, somebody did better than average, the other person did worse than average. That's an easy one, and we could still see that, but let's try and use the z-score to have tougher situations. So let's compare 2 athletes. Let's say, let's compare workers. Let's stick with a worker example. This is kind of sports, even though we're looking at height, and they're both height, but let's look at something completely different. And again, we could do like a weightlifter, how much they lift compared to the other competition, compared to a runner or compared to a high jumper. But let's do a work example. So we've got Rick works in a factory in a warehouse. and processes 37 packages in his shift. The average worker processes 32 packages with a standard deviation of 4 packages. Okay, who else? Now we have Bobby, works in a call center, and answered, let's go, 87 calls. The average worker handles 78 calls with a standard deviation of 10. Compared to their coworkers, who's better at their job? So, again, similar to what we saw up here, we're not being told find the z-score, but we're comparing two different data sets, and the z-score is our way to do that. So for Rick, he does 37. And in this one, I did both of them are better than average. Rick processes more packages than the average. Bobby answers more phone calls than average. But how do we make that distinction of who's better? It's the z-score. So for Rick, we'll have 37 minus 32 divided by 4. That comes out to 1.25. So he's 1.25 standard deviations better than average. And then we'll do similar for Bobby. And for Bobby, we've got 87 minus 78 divided by 10. Notice, everybody, I'm not doing big minus small. I'm doing data value minus mean divided by standard deviation. Data value minus mean divided by standard deviation. I don't pick and choose. I'm putting them where they need to go. That's just a coincidence that these all work out to be positive. And in this one, we get 0.9. 0.9 standard deviations better than average. So they're both good. They both do their jobs well. And it's so tempting to look at smaller numbers here, see bigger numbers here, and to think, Bobby, and we do the work, comparatively, we get Rick is better.